Alright, let's pick up from there where we left off in the last lecture. And now we're going to talk about saturation and equilibrium. Saturated solution. Okay, we've been over this vocabulary a few times now, but that is when we have the maximum amount of solute that can dissolve at that temperature. And when a solution becomes saturated, we're going to have some solid remaining at the bottom. Once this occurs, once the solution is saturated, we have an equilibrium situation. So we have some of the solid dissolving while some of the dissolved solute reforms the solid. So we've got products making reactants and reactants making products, as you see in this image. So this is a very simplified example where they just have AB is what they're calling the solid. That's going to be some ionic compound, and we see it there at the bottom, so we know that this is a saturated solution. Some of that reactant is forming product, which are these dissolved particles, while some of the dissolved particles are reforming the solid. But it's going at the same rate, so that the same amount of solid remains on the bottom in total, and the same amount of ions in solution. So remember, with an equilibrium, we have forward and reverse at the same rate. So your amount of solid at the bottom doesn't change, and your amount of ions in solution don't change. Some of them are swapping places. Alright, let's talk about thermodynamics for a minute. So we've got to put on our thinking cap to remember back to this. This is talking about delta S. What does that stand for? Delta S. Entropy. The entropy for dissolving is actually negative for some salts. Okay, what does that mean? Remember, entropy is disorder. If it is positive, that means your disorder is increasing. And we would expect that if we take a solid salt and dissolve it in water where it all is breaking apart, we would expect that that would make the entropy go up. But in some cases, okay, and this is rare, but in some cases, the entropy, the disorder, can actually go down. And the reason for that is because these ions are now surrounded by water, and the water is being attracted to these ions. If the ions have a large charge, like these do, +2 and -2, and if they're relatively small, remember that attractive force increases when your size decreases. So if they're small with a large charge, these water molecules get stuck around them, and the water molecules actually have restricted motion. So therefore, there is a net decrease in entropy. So overall, our disorder actually can go down because those water molecules are now very restricted in their motion. Remember that decreasing entropy is not favored. The universe favors an increase in disorder. Alright? So for salts with low solubility, the delta G value may actually be positive. Remember the equation for delta G, which we gave right here. If delta S is negative, well, that with the negative sign here will combine to make a positive, right? And then if your delta H is positive, which means endothermic, which most salts dissolving are endothermic because you've got to break those ionic bonds. So we've got endothermic processes breaking apart the ionic salt. If the delta S is also negative, like we saw before with those small ions with large charge, then there is no way that the process can be favored. So delta G will end up being greater than 0, or delta G will be positive. Therefore, the K value will be less than 1. And that K value is your KSP. Okay, so let's kind of put this all together. We're looking at equilibrium situations here. And we're saying that sometimes when we dissolve a salt, the delta G is positive, meaning overall it's not thermodynamically favored. Therefore, our K value is going to be less than 1, so 10 to the negative something. Why would dissolving not be favored? Well, dissolving of an ionic salt is often, most of the time, endothermic because we've got to break apart ionic bonds, and those are normally stronger than the ion-dipole interactions we're forming. Also, when we dissolve some salts, it is actually not favored in terms of entropy because the entropy may go down as the water surrounds those ions. And those two factors put together are going to create an unfavorable situation for dissolving. All right, more equilibrium review here. Q. Remember, Q is written just like K, with our products on the top and our reactants on the bottom, raised to their coefficients. And we don't include solids or liquids, so it's written just like K, but Q is used when you have a question, right, about whether you are at equilibrium or not. And Q is really important when we're talking about dissolving solids because it can tell us something really specific about the situation. And the AP exam people love to ask this question, and they won't necessarily tell you that you need to calculate Q. So we'll have to have a heads up for that. All right, so the question will be, blah, blah, blah is mixed with blah, 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 will a precipitate form? Okay, so if the question is, will a precipitate form, we need to calculate Q, and compare it to K. So here's how it goes. If Q is equal to KSP, we are at equilibrium. So the solution is saturated, and we have solid and aqueous species involved. So we're already at equilibrium. So it's not like a precipitate will form or won't form. We're just already at equilibrium. If Q is greater than K, a precipitate will form. A precipitate will form. Because, remember, if Q is greater than K, the reaction's gone too far. So we've got to go back toward the reactants. And if we're dealing with a KSP, our reactant is always a solid. So that means if we go back toward a solid is a precipitate. So a precipitate will form. However, if Q is less than K, remember, we're going to keep going to the right, and those right is where our ions are, so no precipitate forms. The solution is unsaturated, and all of the ions will remain in solution. So if Q is greater than K, we can say that the solution is saturated, and there's actually extra in there. If Q is less than K, we're not saturated yet, so no precipitate forms. Right, so these are key to keep in mind if they ask us, will a precipitate form? We've got to calculate Q. If it's greater than K, yes, a precipitate will form. Less than K, no, a precipitate will not form. All right, so here is an example. In part A, we want to first find the KSP if we have a saturated solution where our concentration of chlorine is known. The second question is, will a precipitate form, Q, when we mix the sodium chloride, so we've got the chlorine, with the lead nitrate. So we've got the lead. So we're mixing lead and chlorine together. Will a precipitate form? Well, we got to calculate Q to figure that out. We want to assume that the temperature is the same as part A, because if the temperature is the same, then we can use the same K value that we're going to calculate in part A. Alright, so I'm going to flip over where you can see me writing, and we'll work this problem out. Keep the problem in front of you to refer to. Alright, first of all, remember from last time we talked about they're not going to ask you all the time to write the reaction. They're not going to ask you all the time to write the equilibrium expression, but we need to do so. So I'm going to start by writing the reaction of lead chloride in terms of its KSP. So there's my lead chloride. Always with KSP, that's your only reactant. Double arrow, lead plus 2. And we're going to make 2 chlorides out of that. Right, this is a solid, so it's not involved on my rice table. Okay, I'm also going to go ahead and write my KSP expression. So KSP equals my lead plus 2 and my chloride to the second power. In the problem, it says that they have a saturated solution. So when I have the saturated solution, that's when I'm at equilibrium. Okay, saturated solution is an equilibrium situation. I start with water, so I don't have any of these. And now I have a saturated solution, and it has 0.0325 as the concentration of the chlorine. Same thing I did before, plus x and plus 2x on my E line, and then this one is just x. Alright, I know my concentration of my chlorine, and I know that it started out at 0, because I'm starting with just pure water, and now I have a saturated solution, and it's plus 2x. So 0 plus 2x led me to this concentration. So that can be an equation. 0 plus 2x equals 0.0325. So I need to know what x is. X is 0.0325 divided by 2, right? So x must be 0.01625. That's the concentration of my lead. That's not what the question asked for, though, right? The question asked for KSP, right? But I needed this information to find KSP, because KSP is equal to my lead concentration, which is X, times my chlorine concentration, which is 2x squared. Okay, so now we can solve for KSP. So it's going to be 0.01625 times 0.0325 squared. Remember, our K values don't have any units. So KSP equals 0.01625 times 0.0325 raised to the second power. So I got 1.72 times 10 to the negative 1, 2, 3, 4, 5 as my KSP value. Alright, so this again is what they ask us to solve for in A. They did not ask me to write the reaction, but I always do if I'm dealing with a KSP, and I always write the expression as well. This will be the start of my ice table or rice table. And they gave me, this is the only piece of information they gave me right here. So from that, I said that must be 2x. So I solved for x, which was my lead. Then plugged those values into my KSP expression and solved. Notice this KSP is less than 1. So I know that this reaction is not thermodynamically favorable. My delta G must be greater than 0 or positive. Alright, good with that? Now let's look at B. This time they're asking us, will a precipitate form of PbCl2? Okay, so will a precipitate form, we've got to compare KSP to Q. Alright, so our Q is going to be written the exact same way as our K. That's why it's also important that we write our K expression. We got to write Q the exact same way as our K, but we're going to use the values that were given because we don't know if we're at equilibrium. Okay, so we need our lead concentration and our chloride concentration in situation B. Alright, so let's flip back over to the paper and explore that a little bit further. This is the work for part A. If you want to pause it and make sure you got that. They do not show the ice table. Okay, what they do instead is they're kind of doing the ice table in their head. This is 2 chlorine, so that must be 2s or 2x, depending on how you look at it. And this is your lead. Okay, so that's just your S. We knew the chlorine, so they plug it in. They don't multiply it by 2. Okay, it is the chlorine concentration. What they do instead is they multiply it by half to get the lead, which is exactly what we did on the ice table. And they plug those in to find KSP. Alright, let's go back again and look at part B. So the question, will a precipitate form? That always means that we're looking for Q for this KSP. Okay, so even though these things seem to be our reactants, we have to write Q just like we wrote KSP. So we have to write it using that KSP equation, which is the lead chloride dissolving. Okay, so what we need from this is we need our chloride concentration and our lead concentration. And we are given the chlorine concentration and the lead concentration, but we're given those before they get mixed together. So originally we had 200 milliliters of this and 100 milliliters of this, but now they're mixed together. So that changes my volume. So now my volume is not 200 milliliters, it's not 100 milliliters, now my volume is 300 milliliters. Alright? So if you remember back to lecture 1, we talked about if you have a solution and then you add water to it, which is essentially what we're doing here, even though the water has other stuff in it, it changes the concentration, and it's known as a dilution. So we've got to calculate the new concentration of these two species. Do you remember what equation to use in a dilution? We're going to use that equation M1 V1 equals M2 V2. Alright, so let's start with the chlorine in sodium chloride. So there's one chlorine in every one sodium chloride. So the concentration in the beginning is the same. 3.78 times 10 to the negative 2 is my molarity, and I start with 200 milliliters of that. I need to figure out what the molarity is now, M2, that I have 300 milliliters total. Okay, so to solve for M2, I'm just going to divide both sides by 300 milliliters. And I find that the new concentration of the chlorine is 0.0252 molarity. Alright, so now to calculate the lead concentration in the solution, originally its concentration was 2.45 times 10 to the negative 2 inside the lead nitrate. Lead nitrate has one lead in it, so the concentration of the lead would be the same when that dissolves, and that was in 100 milliliters of that solution. And we need to know the concentration now that we have a total of 300 milliliters. So we'll divide both sides by this 300 milliliters to find our new molarity for the lead. So 2.45 times 10 to the negative 2 times 100 divided by 300. I'm getting 0.00817 molarity for my lead. So now I have my chlorine concentration and my lead concentration. And remember the question was, will a precipitate form? So when we're asked that question, we're calculating Q for the precipitate that we think would form, which is going to be our lead concentration and our chlorine concentration squared, just like our KSP expression earlier. And we'll plug in our values. Our lead concentration we know is 0.00817, and our chlorine concentration 0.0252 squared, and that gives me a Q value of 5.19 times 10 to the negative 6. Okay, as my Q. Now again, this is not the answer. Okay, the question was, will a precipitate form? So we've got to look at our K value that we got from part A and compare it to this Q value and figure out if Q is greater than, less than, or equal to K. So we previously found that the KSP value was 1.72 times 10 to the negative 5th, and here we have our Q value. our Q value is less than our K value. So that means that we have not reached the saturation point if Q is less than K. So therefore, no precipitate will form. Right? So this is the way we work a problem when it asks, will a precipitate form? We've got to find the concentration of both the species that would be involved in the precipitate formation, calculate Q, and then compare that to our K value.